Hello, everyone. So in this particular video, we're going to talk about really the last type of computation that we do in the course. After this, we rehash everything, doing it in a more abstract sense. It's the exact same results. It's just that we do it with abstract objects. So this is called orthogonal diagonalization. Just want to review first the diagonalization theorem so you understand where we're going. So if you give me an n by n matrix with k distinct eigenvalues, the following statements are all equivalent. So then the matrix is diagonalizable. That means there's a matrix Q, which is a matrix whose columns are eigenvectors, and a matrix D, which is a matrix, a diagonal matrix whose entries on the main diagonal are eigenvalues. So that the inverse of the matrix of eigenvectors inverted times A times Q is equal to the diagonal matrix. Then it's also equivalent to saying that we have enough eigenvectors, that A has to have n linearly independent eigenvectors. We also have that the union of the bases of the eigenspaces contains n vectors. This is an interesting little detail because in this part of the proof, I actually showed you that if you have n eigenvectors that are linearly independent and you take only those that correspond to a particular eigenvalue, it's actually a basis for that eigenspace. And then we had one last one, which is that the algebraic multiplicity is equal to the geometric multiplicity for every single eigenvalue. Now, the thing about this theorem, though, what it doesn't say is what the matrix Q is like. I would really like that the matrix Q, the matrix of eigenvectors, is really easy to find its inverse. So for that reason, we go beyond just mere diagonalization to what we call orthogonal diagonalization, or orthogonally diagonalizable. We say that a matrix is orthogonally diagonalizable if there is an orthogonal matrix Q that will then actually diagonalize A. So then this matrix Q, its transpose is the inverse. So the equation Q transpose times A times Q equals the diagonal matrix is actually a similarity relation between the matrix A and the diagonal matrix D. Q is still a matrix of eigenvectors. D is still a diagonal matrix whose entries are eigenvalues, and they correspond to each other. The ith column of Q is an eigenvector, and the ith entry on the main diagonal is its corresponding eigenvalue. So I just want to show you an example. So for example, this one matrix is diagonalizable, but when you go through the process of diagonalizing it, you get the eigenvalues of 1 and 3, and the corresponding eigenvectors are x1 and x2, as I have here, 1, -1, and 1, 1. Notice that those two vectors are actually orthogonal to each other. And if you have vectors that correspond to a basis for a space, you can always multiply those vectors in that basis by any scalar you want, and you don't actually go change the span of that set of vectors. All you do is change the entries. So for that reason, I can take each of these vectors and I can divide by their lengths, and I still get eigenvectors for their corresponding eigenvalues. So I do that. I take the vectors x1 and x2, I divide each by their lengths, and I form the matrix Q, which is just those columns. I just chose a certain order. I also decided to factor out the 1 over the square root of 2, just to make it look easier or look simpler. But if you take this matrix, it's actually orthogonal. It's an orthogonal matrix. That's because the columns are orthogonal and all of unit length. So they form an orthonormal basis for R2. So then the inverse of Q is Q transpose. So if I just form the similarity relationship, I take Q transpose times A times Q, you actually get the diagonal matrix whose entries on the main diagonal are 1 and 3. So that matrix orthogonally diagonalizes the matrix. It's neat, right? So what we want to know then is when can we do this? Under what condition, when it's true, can I guarantee that the matrix is orthogonally diagonalizable? And if the matrix is orthogonally diagonalizable, what can I say about the original matrix? So the answer is it's really easy to see when it's true. So the condition is wonderful, but I'd like to spend a little more time first on talking about some properties that would have to also be true before we get to the big theorem. So there's two main results that we need along the way. The first one is that if A is orthogonally diagonalizable, then the eigenspaces themselves are orthogonal to each other. That means if you take an eigenspace for one eigenvalue, take an eigenspace for a different eigenvalue, take any two vectors in here and compare them, they're always orthogonal to each other. Why is actually coming right from the diagonalization proof that I gave before, just taking it one step further. So suppose that the matrix is orthogonally diagonalizable. That means it's diagonalizable. So there's a matrix Q of eigenvectors, of which there are n that are linearly independent. But if it's orthogonally diagonalizable, then those eigenvectors are actually also, therefore, orthogonal to each other. That means then that Q transpose has to equal Q inverse. And it also shows then automatically that A is similar to D. Consequently, that means then, as I was saying before, that the columns of Q have got to be, well, they have to be orthogonal eigenvectors. All I want you to do is among that set of orthogonal eigenvalues, follow the proof like I did before for the diagonalization theorem, and just find all the eigenvectors that correspond to one eigenvalue. And then do the same for a different eigenvalue. So you get two sets of eigenvectors. From the proof I gave you, each set of eigenvectors from this set of n orthogonal eigenvectors will form a basis for the corresponding eigenspace. But all these vectors are orthogonal to each other. All of them are orthogonal to each other. So because of that, then, the basis for one eigenspace and the basis for the other eigenspace, since all these vectors are orthogonal, of course, the eigenspaces are orthogonal to each other also. So that's one easy result. That's nice to remember so that we don't have to spend too much time worried about that the eigenspaces, that their bases are actually orthogonal to each other in the process we're about to do. Another thing, well, or just a quick example. If you look at this matrix 1, 2, 1, 1, 2, it has the following eigenvalues, which are 1 and 3. And notice that the matrix here, Q, which is 1 over the square root of 2 times the matrix 1, 1, negative 1, 1, that matrix is orthogonal, and it orthogonally diagonalizes A. So since A is orthogonally diagonalizable, look at the eigenspaces created by 1 and 3. They are spanned by the corresponding eigenvectors. Clearly, any vector in E1 being a multiple of 1, negative 1, and any vector in E3 being a multiple of 1, 1, they are clearly orthogonal to each other just by taking their dot products. So the eigenspaces are orthogonal to each other. I can do one more thing too, that if you give me any symmetric matrix, give me any real symmetric matrix, then when you find the eigenvalues and corresponding eigenvectors for that matrix, they're actually all real. This is important because it's completely possible that when you find the characteristic polynomial, that when you solve that to get all the roots, some of those roots might be complex numbers. And then of course, the corresponding eigenvectors would also be complex, have complex entries. But we're guaranteed though, as long as the matrix is real and symmetric, that won't happen. I'm choosing not to prove that. The reason is I don't want to go through the process of teaching you guys some complex analysis or just basic complex number arithmetic, as it's likely that you don't see it anymore, not at least in college until much later. So we're just going to go with I believe and move on. So as an example, remember that matrix 2, 1, 1, 2, it was orthogonally diagonalizable, but it also happened to be a real symmetric matrix. So when you looked at its eigenvalues, they were real. And if you look at the eigenvectors, they were real. So I believe this is enough for this video.